Chapter 11 focuses on modeling randomness. Statistics is the explanation of variation in the context of what remains unexplained. That is the way that our textbook defines statistics back in Chapter 1. So far, our focus has been largely on the portion of variation that can be explained by the explanatory variables in the model. We have started to talk a little bit about statistical inference and making confidence intervals, but we're going to be focusing much more on thinking about sort of margins of error and how confident we can be in our predictions, and also on testing hypotheses. And these types of inference are going to require us to think much more about the residual variation, the part that's left unexplained by the model. In order to sort of start working in this realm, we're going to need to think a little bit more about probability first. So we're going to, in this chapter, focus on the idea of probability models. Now, before we talk about probability models, just quickly remember that probability is a number between 0 and 1 that indicates how likely an event is to occur. And a probability of 0 would indicate that the event would be virtually impossible or impossible. And an event with probability 1 would be certain to happen. A probability model is a model that is going to assign probability to the outcome of random events. So in order to kind of think about some of this language, I want to talk for a minute. So an event is just a phenomenon that produces some sort of random outcome. Something like a coin flip would be an event. Although the event is random, there are certain structures associated with that event. One of them is what the possible outcomes of the event are. In this case, the possible outcomes are that it could land with heads or with tails facing up. And that set of outcomes is called the outcome set. You may have seen this called a sample space or an outcome space in another course. A probability model just assigns probability to each outcome in the outcome set. So for instance, for the coin flip model, we could define the probability model is that the coin lands with heads facing up with probability 0.5, and lands with tails facing up also with probability 0.5. It's important to remember that since one of these events must occur, one of these outcomes must occur, that the total of the probabilities has to sum to 1. Now we're going to distinguish between a statistical model and a probability model. A statistical model is one that describes the relationship between different variables, while a probability model is what we were just talking about, describes the likelihood of each possible outcome of a random event. A random variable is a numerical outcome that is associated with a random event. There are two types of random variables. Discrete random variables are random variables for which there are a countable number of possible outcomes. So for example, our coin toss, right? There were two possible outcomes, heads and tails. Now, you might be thinking, okay, but those are not numerical outcomes, but I could code them so that it receives a value of 1 if heads and 0 if tails. And if I define my random variable x this way, that would be a discrete random variable. But other things that could be discrete random variables are anything that you could count. Things like the number of siblings that a person has would be a random variable. Now, the other type of random variable is a continuous random variable. Continuous random variables are ones for which the outcome could take any value in an interval of real numbers. So, for example, we might have a situation where we wanted to randomly select a potato from a bin. and record the weight. The weight would be a continuous random variable. So generally speaking, continuous random variables are things that we measure, like time, weight, things like that, whereas discrete random variables are often things that we can count. There are many common models that have already been derived that are useful for fitting a variety of common sort of setting types, and we're going to look at a few of them today. First we'll look at some discrete distributions, the binomial and the Poisson, and then we'll look at some continuous distributions, the continuous uniform, the normal distribution, and the exponential. The binomial distribution is useful when we are counting the number of successes that occur in a fixed number of independent trials. It's important that the number of trials, n, is fixed before in the setting. That there are two possible outcomes for each trial, which we consider to be success and failure. And what we're counting is what we're going to call success. P, the probability of success, is got to be the same for each of these independent trials. And if we let x equal the number of successes that occur in the n trials, then x will have a binomial distribution. Now, because we're counting how many successes occur in n trials, we could have anywhere from 0 successes to n successes. And so the outcome set is the integers 0, 1, 2, and so on up to n. Now, an example of a binomial distribution, or a setting that could be modeled by a binomial distribution, would be this one. According to the U.S. Census Bureau, 80.6% of Vermont households have broadband internet. We randomly select 50 Vermont households. If we let x be the number of selected households with broadband internet, then x will have a binomial distribution with n equals 50 and p equals 0.806. Now, it's reasonable to use a binomial here because we have a fixed number of trials. We know we're choosing 50 households. They're independent of each other because they're randomly selected. And also because they're randomly selected, we know they should be sort of equally likely to have broadband internet and have the same probability of success, 0.806. Now, a couple of things we'll explore a little bit later. The binomial distribution, it's a distribution of a random variable. Random variable has numerical outcomes, so we could think about graphing the distribution of the random variable. And as we'll see later on, the shape of the binomial distribution, as well as where it's centered and how much spread there is going to be related to both n and p. And it's going to change quite drastically depending on the values of n and p. So we'll take a look at that later on. The Poisson distribution is also useful for count situation, but it's useful instead of with a fixed number of trials. It's useful for counting the number of events that occur independently of each other in an interval of time or possibly of space. If we let x equal the number of events that occur in the interval, we know that we could have 0 events occur in an interval, and we could have potentially any positive counting number occur in that interval. And the parameter that we use to specify, which member of this sort of Poisson distribution family we're working with is called lambda, and lambda represents the average rate. So how many events on average occur in an interval. A setting that could be modeled with a Poisson distribution would be one like this. According to the U.S. Weather Service, there are an average of 5.5 hurricanes in the Atlantic Ocean per year. If we let x equal the number of hurricanes that will occur in the Atlantic Ocean this year, we could model this random variable x as a Poisson random variable with a rate, lambda, equal to 5.5. So starting looking at continuous distributions, the first one we'll talk about is the continuous and uniform distribution. This is when we have a random value is generated that's equally likely to be anywhere in a range of values. The parameters that we need to know are what the lower and upper limits of that range of values might be. We'll call those A and B. X is the value that we're selecting. So we know that X is going to have an outcome set that is the values between A and B. So for instance, a spinner is spun and we record the angle from a reference line when the spinner stops. So picture the spinner with the reference line. So here we can see our reference line, and here we can see the angle between where the reference line is and where the spinner stops. So since there are 360 degrees in the circle, this angle has to be somewhere between 0 and 360, and it's probably a reasonable model to think that it's equally likely to be in any of those places. Normal distribution is probably common to most of us. It's a bell-shaped curve. All normal distributions look essentially the same. They have the same nice bell-shaped shape to them. The only difference is where the bell is centered and how spread out they are. So normal distribution is useful when we have a random value generated from a bell-shaped distribution, and we need to know what the mean is, where that distribution is centered, and what the standard deviation is, how spread out the distribution is around that mean. Theoretically speaking, when we select the value x, it could take any value between negative infinity and positive infinity. That's sort of the theory of the mathematical function of the normal distribution, has that range. However, in reality, we often use the normal distribution as a model for things that do not have an infinite range like this. For instance, the height of 14-year-old girls. It's really not possible to have a girl who has a height of negative infinity or even 0, right? But it's a useful model in a lot of situations because the distribution, the probability of the values gets sort of tiny, 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 so close to 0 when you get very far out in the tails that it really doesn't have any meaningful probability outside of sort of a set range. But still, technically speaking, that's the range for the normal distribution. Another continuous distribution that we'll look at is the exponential distribution. The exponential distribution is one where we can look at the time between events that occur independently with an average rate. So remember, the Poisson was counting how many events occurred in an interval. When we have events occurring in a Poisson distribution for the counts, the time between events has an exponential distribution. The average rate is the same that we had for our Poisson, the lambda, and that can be used to parameterize our exponential distribution. And since it's the time between events, between events can't be less than 0. So we have that x has to be greater than 0. And another example here that would be a setting we could model with an exponential distribution would be that calls arrive at a dentist office with an average rate of 10 per hour. we let x be the number of hours until the first call arrives after the office opens in the morning, this would have an exponential distribution. My lambda for my exponential distribution, measuring in hours, I need to think about the average rate per hour is 10. Something to be aware of is that when you're working with the exponential distribution, you have to be careful to pay attention to your rate and your time measurement being in the same units. So if instead I decided to use the random variable y, which is equal to the number of minutes until the first call arrives, then I'd need to use a different rate. I have 10 per hour, 10 per 60 minutes, which would equal 1/6 per minute. Whoop. So my lambda here would be 1/6 if I wanted to look at the distribution of the number of minutes until the first call arrived. So just something to be a little bit careful of when you're working with the exponential distribution, to pay attention that the units that you're using for measuring time are the same as what you're using to calculate the rate. Okay, so next I'm going to sort of talk through the common probability calculations that we can do with R. There are some exercises here, and rather than go through the exercises on this recording, I'm going to make a separate recording that's going to work in our studio, and we'll go through those exercises. So look for the second video to actually go through the R with you. But for now, let me do a quick talk through here. When we're working in R and we want to use one of the common probability models, there is a model name that's associated with each of them. So for instance, the binomial, the model name is BINOM, binom. And there are also certain parameters that we need to enter so that the binomial knows, okay, in this family of binomial models, which one am I working with? And so remember, for the binomial, we needed to know n and p, size was n, and probability is our p that we talked about before. For the Poisson, we needed to know lambda. For the uniform, we need to know the minimum and the maximum values. For the normal, we need to know the mean and the standard deviation. There's also the log normal that we're not really going to use here today, so it's in here, but won't continue with it. And then the exponential model has the model name EXP, and we need to enter the rate when we're using that, and the rate is what we again were calling lambda before. So it's kind of funny when you're using the Poisson model, you call the rate lambda, and when you use the exponential model, you call the rate rate, but that's what you have to do. Okay, so I want to see sort of how we work with these a little bit. So again, there's some exercises to try, and I'll talk through those in a separate video. The next type of calculation we might want to do is a quantile. For a quantile, we're putting in a probability P, and we're going to get out a value of the random variable x, and it's going to be the value x so that the cumulative probability, the probability that our random variable takes a value less than little x, is equal to p. So, for example, what value x has the probability that the random variable is less than x equal to 0.25, something like that. Now, to do this, we use a Q for quantile in R, and then we tell it the model name, which depends, of course, on the setting. We tell it the probability that we're interested in. In this case, that would be 0.25. And then we tell it the values of the parameters that are needed depending on the model. So for example, if we want to find the average number of hurricanes per year in the Atlantic, we know that that average number has a Poisson distribution with an average of 5.5 events per year. We could find a 95% coverage interval. A 95% coverage interval, remember I'm going to be finding the places where I've got 95% in the middle, which means I'm going to be looking for 0.025 in the lower tail and 0.975 is going to be the cutoff for that upper tail in terms of the cumulative probability. So I put in the Q for quantile. It's a Poisson distribution, so I put in the Poisson. Now I need to tell it the values P that I want. Since I want two different values, I'm going to give it a list, 0.025 and 0.975, but in order for R to handle that list, I'm going to put it in parentheses and put the C in front of it. So this is telling it that I want those two values for P. And then because the Poisson is parameterized with lambda, I need to tell it what lambda is. The output from this gives me a lower limit of 1, an upper limit of 11. So assuming that this probability model is correct, there's a 95% chance that there will be between 1 and 11 hurricanes in the Atlantic Ocean next year. And again, here's another situation for you to give a try, and we'll take a look at that later in the other video. Next thing we might be calculating with R is cumulative probability, or a percentile. In this case, instead of putting in the probability and getting out the value, we do the opposite. We put in the value of the random variable that we're interested in, and the output is going to give us a probability that the random variable takes on a value at the value little x or less. So for instance, I'm putting in, if I have a nice normal distribution or something like that, I'll be putting in x and figuring out what this is down here. Sorry, okay. To do this in R, I use a P, right, for percentile. I enter the model name again. I tell it what the value is that I'm looking to see what the probability is that the random variable takes a value less than that. And then I tell it the parameters that are needed for the particular model. So another example. A hotline receives calls at an average rate of 3 per hour. I want to know what is the probability that the wait until the next call is less than 15 minutes. Now, since I'm looking at the wait in minutes, but the rate is in hours, I have to either change my minutes to hours or change my rate per hour into a rate per minute. I'm going to change my number of minutes into hours. So this is 1/4 of an hour, or 0.25 hours. So I want to know what is the probability that the wait is less than or equal to 0.25 hours. I can find that by taking the P for percentile. Since it's an exponential model, the time to event in a Poisson process, use my exponential. I put in my x value, which is 0.25. Then I type in my rate, and it gives me the probability. And again, I'll go through these you try it activities. These are the ones that are on the handout. So I do suggest you go through and give them a try, and then I'll work through them and talk about the solutions on the other video. If I'm working with a discrete distribution, I can also find the probability of any exact outcome by using this percentile. The reason that I can do this is because, remember, for discrete distributions, I have countable outcomes. And so if I'm looking at a countable outcome type of situation, the probability that x is less than or equal to little x minus the probability that x is less than or equal to that value, little x minus 1, is going to give me the probability that x equals x. And to make this clear, you can kind of think about it this way. If I take the probability that x is less than or equal to 3 minus the probability that x is less than or equal to 2, if I'm, say, counting something, x can take the values 0, 1, 2, 3, 4, and so on. The probability that x is less than or equal to 3, if I take away the probability that x is less than or equal to 2, the only thing that leaves me is 3. So this can be used to find probabilities with discrete distributions. I'll just mention that for continuous random variables, because we can take any value in a range of values, it's actually sort of theoretically the probability of any exact value occurring is 0. So that's a situation where even the outcomes that do occur, technically speaking, have 0 probability. When we're working with continuous random variables, rather than thinking about the massive probability at an individual point, we think about probability in a range of values. So for something like a normal distribution, we're using the area under this curve, continuous curve, to represent the probability. And at an exact point, there's no area under the curve. But if I make an interval between x and y, say, there's probability in between. So I can only talk about the probability that the random variable is between little x and little y having positive probability. The probability that it takes on exactly either of those values is 0. And it's not a super important point for the purposes of this course, but some of you have probably already seen that in your probability classes, and I'll just mention it. Okay. And again, have an exercise for you to try doing that in R, which I will work through in the other video. So just a little preview for the topics of the videos that will be posted next Tuesday. One is just to sort of look and see that each distribution of a random variable has a mean and a variance. So we'll learn a little bit about means and variances of random variables and about means and variances of sums of independent random variables. So we'll take a look at that. Another thing that we'll be looking at on the videos posted for Tuesday is looking at the fact that the sample mean is actually a random variable in and of itself, and we can describe the distribution of the sample mean, which is then going to be useful for making inferences. So hopefully this video helps you. As a review, if you were able to attend the live lecture, and as a substitute if you couldn't, keep your eyes out for the second video that's going to work through the solutions to the R portion. Thanks. Have a good day.